Hello, mathematicians. As we start this new chapter on polynomials, we're going to first start off by reviewing exponent properties. This is stuff that we've learned in Algebra 1 in the past, but we're going to relearn it, we're going to review it, we're going to evaluate and simplify exponent expressions. Now, the key thing to all these properties that we're going to be reviewing is that all of it we can figure out ourselves. I'm going to show how we derive every single one of these properties so that you can actually reconstruct it if you ever forget. So let's look how we can evaluate this expression here, and let's first expand it out using what we know is the kind of definition of exponents. 2 to the third is repeated multiplication of 2 3 times. 2 to the fifth is multiplication of 2 5 times. And if we count them all up together, we have 3 of these, we have 5 of these, and now we can bring this together into one exponent term, 2 to the 3 plus 5, because we have 8 2's all together, and now this becomes 2 to the 8th power. So we can generalize this into kind of a property that when we have two exponent terms of the same base, we can add the exponents together. Now we have another property here. These two are different properties. These are different. So be careful here. This is the multiplication of two exponent terms. This is power to the power, which is different. Now let's expand the inside of the parentheses first. This expands to 2 times 2 times 2 raised to the 5th power, and now let's expand this all out, repeating 5 times this 2 times 2 times 2. Now we don't want to write this all the time, but we can actually count up all the 2's in this manner. We realize that we have 5 sets of 3 that can be represented as 3 times 5, so we can write this as a single exponent, 2 to the 3 times 5 power, 2 to the 15th. Now we can generalize this into a property. I have a to the m to the n power is equal to the product of a, or a to the product of m times n. Let's look at another property here. Two numbers all raised to the 3rd power. Product of two numbers raised to the 3rd power. Let's expand this out. 2 times 3 times 2 times 3 times 2 times 3. We do some regrouping by the commutative property of multiplication, and I have a group of 2's and a group of 3's, and I have 3 of each of these. Now I can write each of these as exponential terms, 2 to the 3rd times 3 to the 3rd. And now here we have another generalized property. Product of two numbers raised to the power is equal to a to the m times b to the m. It's kind of, you could think of it as distribution of this exponent across each one of these multiplicative terms. Now, we learned earlier that division and multiplication are very, very similar. In fact, division is multiplication of the reciprocal, so we should find very similar properties here. And indeed, that's what we find. If we expand this out, we have 2/5 to the 3rd power. We just multiply it 3 times against itself. We can regroup this as well, 2 times 2 times 2 over 5 times 5 times 5, and we get 2 to the 3rd divided by 5 to the 3rd. And now we can write this as a general property. When I have a divided by b raised to the m power, I can rewrite this as a to the m divided by b to the m. And of course we can go both directions. If I have something in this form, I can convert it into this form. If I have something in this form, I can convert it into this form. Okay, let's look at some more properties. Now I have division of two exponential terms. Let's expand these out as well. I have 7 terms of 2 here. I have 3 terms of 2 down at the bottom. And now I can cancel. I can reduce. Each one of these 2's reduces into 1 and basically disappears. I'm left with 4. I can express this as 2 to the 7th minus 3 because I had 7 up here, 3 down here, but I can get rid of 3 in a sense. So now I have 2 to the 4th power. So we could generalize this. A to the m divided by a to the n is equal to the a to the m minus n. Now this brings up some pretty interesting other properties that are very important to see. Let's try this. 2 to the 4th divided by 2 to the 4th, and now let's use this property here where we're going to subtract the exponents. So now I have 2 to the 4th minus 2 to the 4 minus 4. 4 minus 4. That's equal to 2 to the 0. And 2 to the 0 is equal to 1. Why? Because 2 to the 4th divided by 2 to the 4th, something divided by that same exact thing is always equal to 1. So we have this interesting property that something raised to the 0 power is equal to 1, and that's our property over here. A number raised to the 0 power is always equal to 1, no matter what a is. Now we have another property. 2 to the 0 divided by 2 to the 4th. Let's kind of, again, use this subtraction property here, or this quotient property as I'll call it. We could rewrite this expression right here as 2 to the 0 minus 4, 0 minus 4, which we can write as 2 to the negative 4. And what does this equal? Well, if we look at the very first term, 2 to the 0 power we recognize as 1. 2 to the 4th power, I just brought this over. So now we have this other interesting relationship here. 2 to the negative 4th is the same as 1 over 2 to the 4th power. This is a very important relationship. We can generalize this over here. A number raised to the negative m power is equal to 1 over that number to the m power. So now let's look at how we can use these. We're going to practice using these properties, and we're going to simplify expressions with exponent terms. And what that means is that we want to translate or simplify expressions such that it contains only positive exponents at the end. So let's start with a simple example. Here we have this expression that have all these negative exponents. First step I can do, I could take this 5 to the 3rd and in a sense bring it up to the top, and in doing that I turn the negative 3 exponent into a positive 3 exponent. I continue doing that with the next term, y negative 2, bring that to the denominator or the numerator, and I get y squared. Now I can do the exact same thing for the exponent terms that are on the top. I'll bring those to the bottom as well, and in doing so the sign flips every single time. X to the 6th, as I bring it down, the sign flips from negative 6 to x to the 6th. So that's a convenient way of thinking about doing it. All the properties that we learned are used in doing this, but this is a kind of a quick way of applying it, which I want to show. So you can move around negative exponents from the denominator to the numerator or vice versa, and you flip the sign in doing so. Now let's look at this next one. 2 to the 3rd over 5 to the 3rd. I have some x terms on top, I have some y terms on top and the bottom, and I need to combine them now. I'm going to first start off with my numbers. There are no common, the 2 to the third is all by itself, 2 to the third, 5 to the third just comes over here as well. Now I have an x to the second term and x to the fifth term here. The exponent here, 5, is greater than 2, so what I'm going to do is write this as x to the third. And how did I get 3? I took the exponent of 5 minus 2, and I got x to the third here. Now I do the same thing for the y exponent. So let's look at this y exponent term. I get y to the fifth. How did I get that? I looked at this exponent here. It's bigger than the exponent I see down here. This is an invisible 1, you can imagine. So I have 6 minus 1, which is equal to 5. Let's look at another example. I have this expression here. Let's deal with the numerator term first, kind of multiplying this 2 times the negative 3 and the 3 here. So negative 3 times 2 is negative 6. 3 times 2 is equal to 6. Now I'm going to look for like terms, terms with the same base, and combine them. So I have my x term here, and I have x to the fifth, and I have x to the negative 6. 5 is the bigger number, so I'm going to think of it as 5 plus 6, or 5 minus negative 6, and I get x to the 11th on the bottom. And then my y's cancel out here, and I'm left with this as my final answer. Final example. This is the most complicated example. Again, let's just start by looking at all the common bases. I have negative 5 raised to the powers. 3 is greater than 2 in terms of the exponents, so I have negative 5 to the first power. I don't really need to write that one in there. Now let's look at my x terms. I have an x term here and an x term here. The exponent here is a 1, which is greater than negative 5, so that means that I'm going to leave the x on the top. I'm going to think of it as x to the 6th power, which is 1 plus 5. I flip the sign when I bring it upstairs. Now let's look at the y terms. I have my y terms here. Oh, actually, let's look at my z terms here first. Negative 4 is a bigger number than negative 6. So I'm going to bring the negative 6 up to the top. The z to the negative 6 to the top becomes z to the 6th power. So this becomes z squared, which can be thought of as the squared term comes from negative 4 plus 6 here. Now let's look at the y term as my last term. And I have y to the 4th. That comes from 6 minus 2. I have y to the 6th right here, minus 2. I get y to the 4th. Now all of this is still raised to the negative 2 power. So now I need to still deal with this. I'm going to start multiplying these all out. So here I got negative 2 times 1 here, an invisible 1, my negative 2. I have 6 times negative 2 is negative 12. 2 times negative 2 is negative 4. 4 times negative 2 is negative 8. Now I have all these negative exponents now, so I need to fix this. So I'm going to rearrange this. I have my terms that are on the top that are all negative exponents. I'm bringing them to the bottom and negating all the exponents. And same with y to the negative eighth. I bring that to the top, y to the eighth power. Now, the last thing I want to do is simplify this. Negative 5 squared is equal to 25, and so I'm done. Last concept is scientific notation. We can write, scientific notation is a number times 10 raised to some integer power. So here are some examples of scientific notation. You notice that all of these have a single digit in front of the decimal place. It's a number between 1 and 10 times 10 to some power. So if I wanted to convert a number to scientific notation, I want to move this decimal over here, and I'm counting the number of times I move the decimal place. I move it to the left by 4, so I have 2.13 times 10 to the 4th power. Same thing goes when I want to move it in the other direction, the decimal point. If I move it to the right, then it's 2.63 times 10 to the negative 2 instead. Now let's see how we can combine this together when I multiply two numbers. Let's convert both of these into scientific notation first. Now I'm going to multiply my numbers together, 8.5 and 1.2, and I get 10.2. Then I multiply my 10 to the 6th and 10 to the 3rd, and I get 10 to the 9th. I need to convert 10.2 to scientific notation, though, because it violates this rule up here. So now I convert that by turning it into 1.02 times 10 to the 1st, and now I can multiply these exponents together to get my final scientific notation answer. So that completes lesson 5.1. You can try out the problems on your own after this.